Welcome, viewers. Hope you all are doing great. Today's lecture topic is on top level view of the computer components and their interconnections. So the computer has three main components. First one is called a CPU or central processing unit. This is also called a microprocessor. It has two units, arithmetic logic unit and the program control unit. Second major component is the memory or main memory where program resides temporarily, and CPU reads the instruction and data from main memory and execute it. Third major component is called the IO equipments or peripherals. There are many IO peripherals are there like the hard disk, keyboard, mouse, all grouped together and called input output devices or peripherals. And you can see how the CPU is interacting with main memory and IO components. This architecture was given by von Neumann. He was working in Princeton University in the Institute of Advanced Studies, and that's why this architecture is called IAS computer architecture. This is also called a stored program architecture because the program resides in main memory and CPU reads instruction by instruction. And the program control unit actually synchronizes all operations. And this is the architecture of a general purpose computer because the ALU will perform addition, subtraction, division, many different operations as per the control signal received from the control unit. So this concept in software is different. If everything will be hardwired, then we needed different hardware component for different operations. Add will have separate hardware, division will have separate hardware, but software programming concept, same hardware, one hardware, and different control signals are there. So that is the function of the control unit to generate different control signals. Add will have something, one sequence of zeros and ones, and move will have a separate one. And it is interacting with the memory and IO devices, and everything together is called a computer. So this concept is shown pictorially here. If it is only the hardware, then the input is only data and output is the result. But in this case, we need different hardware for different operation. But programming in software, the ALU receives not only data but also control signals, and control signals is generated after the instruction is interpreted by the program control unit. And this is more beneficial because one hardware and many operations. So, if we want to describe the major components more precisely, we draw their diagram in a modular diagram, how many input signals it is taking and how many output signals it is producing. So, memory has many words, it keeps data or instruction as a sequence of zeros and ones, and every word is of fixed length. In this picture it is showing it can accommodate n words, and it is taking four input signal: read, write, address, and data. You can see some arrows are thin, some arrows are wide arrows means multiple bits of signals coming in the input side. Similarly, for IO module, it is taking several input signals and generating several output signal. And CPU also taking instruction code, data, and control signal, and it is also generating address, control signal, and data. So, three main components as I gone through this: control unit and the ALU together is the CPU, and then the input output devices grouped together called IO devices, and for temporary storage of code and result there is main memory. So in a more detailed view, you can see CPU has ALU, arithmetic logic unit. Also, it is showing some registers now. These registers are for temporarily keeping fixed amount of data in the CPU. All these registers, maybe they are 16 bits long or 32 bits long or 64 bits long, and every computer has different number of registers inside the CPU also, because when the data is coming from main memory they need to be in the processor before they get executed by the execution unit. So name of these registers are program counter, which tells which instruction to execute, then instruction register, which holds the instruction before it will be decoded by the control unit, then memory address register, memory buffer register, IO address register, IO buffer register, etc. And main memory keeps instruction and data, and their addresses are also shown 012. It is all implied address. It is not stored in the main memory. According to the position of the data in the memory, their address is determined. And you can also see that CPU interacting with main memory and the IO module. Here, more detailed data flow is shown in this diagram. You can see that main memory, whatever is coming from the main memory, is getting in the MBR, memory buffer register, and from MBR it is coming to IBR, instruction buffer register. From instruction buffer register it is coming to instruction register. Now this instruction will be decoded by the control unit and it will generate control signal. Now, when instruction is executed, the second instruction will be brought from memory. The address of the second instruction is kept in program counter. Program counter is sending the address to memory address register, and memory address register is giving the address to main memory to give that instruction. Okay, so this is the little bit more detail. So you can see execution of one instruction has several steps: fetching the instruction from main memory and then execute it. So we are going to see a execution cycle of an instruction. Here I am showing two instruction: add R1, R2, R3. This is called assembly language code. Add is an opcode, and R1, R2, R2 are called operands. Similarly, in the second instruction, move is the opcode, R1 and R5 are the operands. So in the instruction cycle, the first step is the fetch instruction and then execute instruction, and then it goes to fetch the next instruction, execute it next, and this loop keeps on going until the program is halted. Now, we are also showing you the IAS memory format here. IAS was using a 40 bits memory word, and if it keeps a numeric number, the first bit is for the sign bit. 0 means positive, 1 means negative number, and rest 39 bits will be for keeping the number. And if the memory word is keeping instructions, then one instruction was 20 bits long, so it can keep two instructions here. And each instruction is also divided: first 8 bit is for the opcode like add or move, and the next 12 bits was for keeping the address of the operands. So in the fetch cycle, the program counter holds the address of the next instruction to fetch from main memory. And the processor fetches that instruction uh, from memory location pointed by the PC. And then just after that it will increment the PC by 1. That means then it is the next instruction that will be fetched, and instruction is loaded in the instruction register. Remember that picture where the from main memory it is coming from MBR, from MBR it was coming from IBR, and from IBR to IR. IR stands for instruction register, and then the processor's program control unit will interpret that instruction, whether it is add instruction or move instruction, and send that control signal to the ALU. And in the execute cycle, there may be data transfer between the processor and the main memory, or there may be data transfer between the CPU and the IO module, or it is just simple execution of data in the ALU unit. And it can maybe that execution is for alteration of sequence of operation like jump operation, or combination of the above. And basically the fetch cycle takes more time than the fetch cycle, because it is going to the slower memory. It may have to go there multiple times, one for bringing the operand from there, and second time for storing the result into there. So execute takes more time than the fetch operation. So here we are going to see the whole idea of the total instruction execution process will be clear by taking one example. Here we are going to see three instructions execution. So here the opcode of the instructions are given 0001. This is everything is in binary number, and this opcode stands for load accumulator from memory, and from which address of the memory. So after the opcode, operand address will be written. Then second opcode is 0010. It is used for storing accumulator to memory. And third one 0101. Yeah, this opcode is for add to accumulator from memory. So this we are going to see an instruction format and integer format we have seen before. In this example, we are using a 15 bits, 16 bits memory word. So if it is keeping instruction, first 4 bit is for opcode. That's why these are all 4 bits long, 0001. And the next 12 bits is for keeping the address. Okay, so these three instructions execution we are going to see now. So here it is showing if all instructions are in the memory. This was the first instruction with opcode 1, and second instruction has the opcode 5, the first digit. These are all decimal numbers. If you just convert them into 4 bits of binary, 1 is 0001, 5 is 0101, and the third one is for store 0010. And these are also, you can convert this 9 into binary sequence 4 bits, but we don't need it right now. We can consider them as a decimal number. So this is the address part of the operands 940. So here the memory address is given. It is just showing from 300 address location up to 941 address location. And the first one, because the PC program counter is showing 300, that means next instruction will come from 300 address. So this is coming to IR. So now IR has 1940, and this is getting interpreted. So one means load from this address. So in the second step, it is loading from 940. In this 940, this instruction is kept, and this load is happening in the accumulator. And by the meantime, the PC has been incremented by 1, and because it is a load operation, um, so it is loading in 940 Uh, in 940, this number is there, 0003 was there. So that is coming to the accumulator. Now the second instruction 301 is for adding, 5 was for adding to accumulator, and what it will add, whatever number is there in 941, that will get added. In 941 was number 2. So 2 will be added with 3 and it became 5, and the PC got incremented by 1. Now it is going to execute instruction from address 302. In 302, this instruction is there. The opcode is 2. 2 means store. That means whatever is in the accumulator, that will get stored in 941. So 5 is getting stored in here. Okay, is it understood? If you study this carefully, step by step, the whole sequence will be understood clearly. So here we are going to see the instruction cycle in little bit more detail. Previously we have seen there is one fetch step, another execute step. Now it is shown in more detail. After instruction fetch, instruction operation decoding will happen. Then operand address calculation will happen. Then operand fetch will happen. Then data operation, operand address calculation is again needed. If after calculation you have to store it, then operand store and then it will go back. And here it is showing return for string or vector data. In vector data, instruction is the same, but it will be executed on several data. So that is called vector data. If it is not vector data, it will fetch the next instruction. And if it is vector data, now instead of fetching the instruction, it will be fetching the next operand. Okay, after seeing the detailed execution cycle, we are going to talk about another thing that is needed, and that is called interrupts. What is interrupts? Like when the CPU is executing the instruction one after another, sometime you have seen that user asks the processor to close execution, close the program, or some error happens. The CPU gives a nice notification to the user and then halts the program. So for that mechanism is called interrupts. So interrupt is a mechanism by which other modules like IO may interrupt the normal sequence of processing. So whenever some other components wants the CPU's attention, CPU will stop doing whatever it was doing and it will take care of that component now. So these interrupts are risen by different components like the memory or the IO devices, or there may be some error in the program execution like overflow, division by zero. They need to be taken care of better. Okay, now let's see what is the benefit of interrupt if it is implemented in the instruction cycle and how it is taken care of by the CPU. So in this picture, it is showing how the CPU is taking care of interrupts. So first picture vertically, there are three pictures program flow shown. The leftmost program flow is showing a user program and one IO program. So IO program means it has to do something with the hard disk. It has to store data in the hard disk. And as I said, hard disk is very much slower than the processor. So user program is divided into three parts, 1, 2, and 3 as shown in the figure. And the IO program is divided into two parts, number 4 and number 5. So when user program is running, section 1 is completed, then the next instruction is a write instruction. That write instruction has to access the hard disk, write it. so it is going to slow down the thing. So if there is one write instruction, for doing the write, something needs to be done by the processor, like section 4 of the IO program is done by the CPU. But after that, once the IO command is released, the CPU has to wait, because IO device is very very slow and it is wasting the CPU's time. And after that IO command is done, still some wrap up things the CPU has to do, and that is the section 5 of the IO program. And after that, the CPU will continue doing the user program section 2. And then when another write commands happen, the same thing, it goes to the IO program, section 4 done by CPU. Then the CPU waits when the actual access of the hard disk is happening, and after that is done, CPU still has to do some other things in section 5, and then the user program continues. And this is when there is no interrupt mechanism. Now in the middle it is showing when there is short wait, short IO wait is there. User program section 1 happened, then write is doing IO program 4, then IO command is there. Here CPU was waiting before, but if there is an interrupt mechanism is there, the CPU will keep doing the user program section. Maybe it will not be able to do the entire section 2. It is just doing 2A part. And then when the interrupt will come from the IO devices, it will do the section 5 of the IO program, and then it will do section 2B. This is for short IO wait. And if there is a long IO wait, after when the write was given, write instruction was given, it is doing, CPU is doing section 4. And then when it was supposed to wait, by that time CPU has completed the entire section 2 of the user program, because this IO device is much much slower, and IO interrupt is coming only here. Okay, so in a different way, it has been written in a different way, shown in the different way. uh, Without interrupt, CPU was waiting for the IO command to finish, and when there is interrupt mechanism, CPU is doing section 1, then 4 from the IO program, then 2A. So you can see the total execution time of the program is much less when there is an interrupt mechanism. Interrupt is whenever the IO device will be done, it will let CPU know that it is done. Otherwise, CPU just was waiting for the IO to finish. So, interrupt is a very good mechanism to make execution time of the program much faster. And when there is a long IO wait, so here section 1 is done, section 4 is done, and still, and because there is another write program, no, so CPU cannot progress anymore, and the processor is waiting, CPU is waiting. Only when the write is done by the IO devices, then it can continue section 5 of the IO program, section 2, etc. Okay, so that is the idea of having an interrupt mechanism in the instruction cycle. So this mechanism, interrupt mechanism, is added in the instruction cycle, and processor checks for interrupt. Uh, if no interrupt, fetch the next instruction, and if interrupt pending, then suspend execution of the current user program, save context. Save context means whatever are the values of the register that are saved somewhere, because when If the CPU will be done doing the IO program, it has to continue from where it left off. Okay, so it will reload the register values from memory and start from there. So when the interrupt mechanism is added in the instruction cycle, it becomes like that. And this interrupt mechanism can be enabled or disabled. If it is disabled, there are only two steps: fetch instruction and execute instruction. But when CPU is taking care of interrupts, after execution cycle, it is going to check for interrupts. So this becomes the instruction cycle. Okay, this is again shown in a different way. User program and interrupt handler, which is called ISR, interrupt service routine. Now sometimes multiple interrupt comes and we are going to see that. So this is a detailed view of the instruction cycle with interrupt. The previously we have seen fetch and execute, but you know that we can depict it in more detail: instruction fetch, instruction operation decoding, operation address calculation, operand fetch. This portion you have seen before. Now then there is interrupt check, then taking care of the interrupt, and then it will go to the instruction address calculation. So now we are going to see if there are multiple interrupts, then what happens? CPU can disable further interrupts, or CPU can assign priority of the interrupts, or it can do first come first service. Which interrupt comes first, that will be taken care of entirely, then the second one entirely, like that. But usually some priorities are assigned. Here it is showing multiple interrupts taken care of by the CPU in a sequential fashion. Interrupt X is done completely, then interrupt Y, and then the user program. And when the CPU is doing interrupt X, if that time interrupt Y comes and interrupt Y has more priority than interrupt X, then it will leave the interrupt X service routine. It will do the interrupt Y service routine. After that, it will finish up the interrupt X service routine, and then it will go back to the user program. So here it is showing different interrupts: printer interrupt service routine, communication ISR, and disk ISR. Printer is a slow device, has less priority. That's why when the communication ISR came in between printer ISR, it went to do the communication ISR. And disk interrupt also came at the same time, and because the communication ISR has more priority, so that one is completed entirely, and then only the disk ISR is taken care of, then rest of the printer ISR, and then the user program. So user program has the lowest priority. So, okay, today it is up to this, and we'll continue on a different topic in the next lecture. Thank you for watching.